In this lesson, we're going to learn about solving quadratic equations using the quadratic formula. And a reminder that solving means finding the roots, the zeros, or the x-intercepts. Okay? So here's your new formula. The roots of a quadratic equation in the form ax squared plus bx plus c equals 0, where a cannot be equal to 0, can be determined by using the quadratic formula. So it's just a plug and chug. We have to identify from the equation that we're given what is a, b, and c, plug them in. The only thing is we are dealing with a root, which we haven't dealt with in a little while. So we've got to remember the properties of square rooting. And in our last lesson, we talked about how the square root of a number has both a positive and a negative value. So we're going to look at that as well. Let's take a look at the first example here. Realize we're dealing with exact solutions as well. So that means we're not wanting decimals. Leave everything in fractions, and if you can't find the square root of a number, leave it under the radical, leave it under the root. So in this equation here, I've got ax squared plus bx plus c already set up for me, where a is equal to 2, b is equal to 8, c is equal to negative 5. Let's substitute in for our new formula here. B is 8, so I'm actually going to put in a negative there. Remember, when you're using substitution, use brackets for every value that you're substituting. Plus or minus, that would be 8 squared minus 4 times 2 times negative 5. All divided by 2 times 2. Keep going here, we can start simplifying. We've got negative 8 plus or minus 64 minus 4 times 8 times negative 5 would give me a negative 160, all under the root, all over 4. Remember that dividing line goes across the entire formula. So a lot of students just put it under the radical, and that's not correct, okay? So just be aware of what you're doing as you're substituting. Negative 8 plus or minus 64, that would be plus 160, those two negatives there, divided by 4. Negative 8 plus or minus 64 plus 160 is 224, all over 4. Alright, at this point, I know that I can't find the square root of 224 as a perfect square root. So I'm going to just leave it there. You can start simplifying radicals if you want, but that's not necessary. In this case, we have two roots, which means we have two x-intercepts. Our first x-intercept would be negative 8 plus the square root of 224, all over 4. And our second x-intercept is negative 8. Subtract 224 under the square root, all over 4. So these are just numbers. If you were to actually punch this into your calculator, you would get a decimal value, which is fine. But when we're using the quadratic formula, we usually use it because we want those perfect roots, or exact roots. I shouldn't say perfect, but those exact roots, those non-decimal roots. Let's take a look at another example. I'm looking at this and I see a problem. I want ax squared plus bx plus c equals 0, and this isn't in that format, so I'm going to have to move this 7x, create a 0 pair to get rid of it. Do the same thing to this side. So I've got 6x squared minus 7x, subtract 3 is equal to 0. Now I can identify my a, b, and c, and we can keep going from there. A is 6, b is negative 7, c is negative 3. We can substitute into our formula. We've got negative b, in this case I've got a negative 7, plus or minus b squared, minus 4 times a times c. That's all under the root, all over 2 times a. Keep going. 7 plus or minus 49 plus 72, all over 12. 7 plus or minus the root of 121. I know the root of 121, that is 11. So plus or minus 11 all over 12. So in this case, this is going to look a little bit different, but I still have two roots. I still have two x-intercepts, two zeros. What are they? Well, 7 plus 11 over 12 is one, and 7 minus 11 over 12 is the other. We can go further in this. That would give me 18 over 12 and negative 4 over 12. Can you reduce those fractions? Yes, you can. Do you need to? No, you don't. So those are my solutions. I've got another quadratic equation where I have two x-intercepts, and this is what they are. So instead of graphing to find those x-intercepts, instead of factoring to find those x-intercepts, this is just another tool in your toolbox to find those x-intercepts, and you can graph those. Now you know from previous lessons that we don't always have two x-intercepts. Sometimes we have one x-intercept and sometimes we have none. Reminder here, this would be two x-intercepts because it's crossing the x-axis in two places. This is one x-intercept where we're touching the x-axis, and then an example where there's no x-intercept would be something like that, where it's not touching the axis at all. So the two examples we've done so far are like this. It's a maximum or minimum. It doesn't matter. What we care about there is that it's two x-intercepts. It's crossing the axis in two places. Let's look at an example where we have one root and an example where we have no roots. So again, same as before, A, B, and C, or A is 1, or B is negative 4, or C is 4. X is equal to negative B plus or minus B squared minus 4 times A times C all over 2 times A. So why in this case are we not having two roots? Let's see what happens. So this is now positive 4 plus or minus 16, and that would be minus 16. Interesting. Why do I say that? Well, what is 16 minus 16? 0. Okay, what's the square root of 0? 0. So when I'm adding and subtracting 0, that doesn't change my answer at all. So all I'm left with is 4 over 2, or 2, which means I only have one x-intercept, or one root. Okay, so whenever you have under the square root there, whenever that goes to 0, you know you're only going to have one solution. That square root business, that stuff in there, is called the discriminant. Whatever happens under that square root in that discriminant will determine whether or not you have one root, two roots, or no roots. Let's take a look back for a moment. So if we look at our discriminants here, under the root I had a positive value, under the root I had a positive value. Okay, so if under the root you have a positive value, then you end up with two roots, two x-intercepts. If under the root you end up with a 0, you have only one x-intercept, one root. So what's going to happen to give us no roots? Let's take a look at this last example that'll show us what happens when there are no roots. We're still using our quadratic formula, same as before. Identify A, B, and C. Substitute in. Let's get negative B, oops, not B, I'll put in my 4. Negative B plus or minus the square root of 4 squared minus 4 times A times C. Substituting everything in, same as before, 2 times 3. I got negative 16 plus or minus 16 minus 24 all over 6. Now at this point you should start looking at that discriminant. What's going on under the root? Negative 16 plus or minus 16 minus 24. That gives us a negative 8 square root over 6. And at this point you should be saying a problem. Did we make a mistake? No, but we do have a negative value under the root. So why is this a problem? Well, go ahead and try to find the square root of any negative number, in this case -8, and you're going to get an error in your calculator, and that's because the square root of any number is imaginary. And that's a different section of math where you see these imaginary numbers, which is a lowercase I, but in this case we don't want imaginary numbers because we actually have a quadratic that exists and we need the actual values for that. So imaginary numbers aren't useful to us in this situation. So whenever you get a negative under the root, you can say that there is no solution to the quadratic formula, which means that there are no roots or no x-intercepts. Okay? And that's important. That's a good solution because that means we know that our quadratic function is going to either look like this, or like this, or like this, or like this, right? Somewhere it's sitting there and not touching the x-axis anywhere. That's it for today's lesson. Thanks for joining me.